Good morning, everyone. First of all, I'd like to thank all committee member nominations under the category of a Chemical Engineering Excellence Award. It's my great pleasure to give a talk today. The topic I'm talking about is interfacial dynamics of hybrid materials for energy and environmental applications. At the beginning, I would like to introduce my research interests, which are divided into three parts, including the design and the synthesis of hybrid materials, and the studies of interfacial dynamics for solid, and solid liquid interfaces by ultrafast laser spectroscopy and the scanning photoelectrochemical microscope for diverse energy transformation applications, such as solar energy conversion, electrochemoluminescence, and the waste-to-energy system. Here I want to show you some examples. We use scanning photoelectrochemical microscope imaging to design and optimize hybrid materials, and then by using morphology engineering to make the uniform, pinhole-free, and high crystallinity thin films. Afterward, we systematically investigate interfacial dynamics by using photophysical and photoelectrochemical techniques to fabricate highly efficient and stable energy transformation systems. There are two kinds of hybrid materials we are interested in, including functional metal-polymer materials and organic inorganic perovskite semiconductors. Why we want to study this platinum acetylide polymer is because heavy metal atom platinum can enhance intersystem crossing due to spin-orbital coupling to generate triplet exciton. This photophysical property allows the routine study of triplet states for diverse energy applications such as photovoltaics, solar-to-fuel generations, and optoelectronic devices. We are interested in developing light harvested metal polymers. We prepare a series of polystyrene-based polymers with different platinum acetylide, P2 platinum and PY platinum. P0 is the donor-only polymer. P100 is the acceptor-only polymer. P3 means there are only 3% acceptors in this copolymer. From P0 to P20, the emission of P2 platinum was decreased, and the emission of PY platinum was then produced. Therefore, we demonstrate the energy transfer has occurred from donor to acceptor. Based on the specific photophysical and electrochemical properties, platinum acetylide serves as a potential alternative for ECL devices. For the phenolene diolphin phenolene donor-acceptor-donor platinum acetylide, we confirm the occurrence of a thermally activated delay phosphorescence by temperature-dependent transient photoluminescence. Because the difference of energy levels between triplet platinum phenolene and triplet platinum diolphin is less than 0.5 electron volt, which results in reverse triplet exciton transport. Therefore, this platinum acetylide is potential for the application of ECL devices. Another hybrid materials we are interested in is organic inorganic halide perovskite. Halide perovskite with the ABX-free structure has been recognized as attractive materials for various energy applications. It's because this kind of materials exhibit outstanding electronic properties. Here is the structure of a methyl ammonium lead halide perovskite, which are formed by three components consisting of organic cation, bivalent, and organic cation and anions, with the octahedral phase of a lead iodide. In this work, we developed a heteroepitaxial structure combining quantum dots and the quasi-2D perovskite to create highly stable, pure red luminescence materials. The resulting perovskite LEDs achieve a record-breaking external quantum efficiency of 24.6% and a significantly extended operational half-lifetime of over 6,300 minutes, making it one of the top-performing pure-rate perovskite LEDs for ultra-high definition display today. To enhance the performance of a perovskite photovoltaics, we use a symmetry-driven engineering approach to design a novel axially symmetric molecules (PPY) which facilitates efficient charge transport through a well-organized, long-range order molecule structure. The resulting PPY-based solar cells achieve a record-breaking power conversion efficiency of 26.6% and demonstrate exceptional stability, retaining 94% of their performance over 3,000 hours of use. Furthermore, we develop lead halide bismuth-based halide perovskite by heterostructure engineering. During the formation of a BPP5 heterojunction, a portion of a BPP0 was formed at the early stage. By adding 5% BMF in solvo-thermal process, the protonated amine ion generated through DMF hydrolysis and then reacted with unreacted bismuth ions, leading to the in situ formation of a BPP5 perovskite heterojunctions. The arc radius of a heterostructure BPP5, the red curve, was considerably smaller compared to other bismuth-based perovskite. Accordingly, heterostructure BPP5 possess a lower charge separation resistance, thereby implying an improvement in the charge separation and transfer between the interfaces. Through a torque plot, we then determine the optical bandgap energy of all powder samples. Based on the energy level diagram, the heterostructure BPP5 showed a high potential for hydrogen production and iodine oxidation as a result of enhanced spatial charge separation. By using bandgap engineering, we developed the perovskite photocatalyst with a bandgap funnel structure as verified by SEM EDAs and the DFT calculation. The bandgap funnel structure means the bandgap is smaller in the surface area and become larger in the interior section because the concentration of iodine ions, the yellow dots, decreases gradually from the surface to the interior. We demonstrate the bandgap funneling in perovskite photocatalyst give rise to improved photoluminescence lifetime, the red curve, increased transient photocurrent, and enhanced hydrogen production. To further understand interfacial dynamics at the solid-solid interface for bandgap funnel structure in perovskite photocatalyst, we measure temperature-dependent transient photoluminescence with temperatures ranging from -30 to 30 degrees Celsius. Based on the classical Marcus theory combined with Arrhenius equation, we certify the mixed halide NbCl-I with the bandgap funnel structures shows stronger electronic coupling and lower activation energy, resulting in enhanced exciton transport. To further understand interfacial interactions at the solid-liquid interfaces for bandgap funnel structures, we measure CV at different scan rate for NbCl-I and Nbi at different scan rates. And then we demonstrate the NbCl-I with bandgap funnel structure shows higher diffusion coefficient and more rapid red constant compared to MBI single halide perovskite. Due to an increase in exciton binding energy by reducing the dimensionality of perovskite semiconductors, we remarkable increase in photoluminescence quantum yield could be observed for solid-state electrochemoluminescence. Lower-dimensional CS4PBBr6 halide perovskite exhibit fairly strong green PL with a quantum yield up to 45%, which is 2 orders of a magnitude larger than its three-dimensional counterparts CSPBBr3. Solid-state CSPBBr6 emitters were cast on glassy carbon electrode to conduct electrochemical measurement and then explore the photophysical behaviors. According to excellent electrochemical and photophysical properties, zero-dimensional CS4PBBr6 is promising to act as an efficient ECL emitter. We then alternatively apply cathodic and anodic potential to produce radical anions and radical cations. The ECL emission is finally produced by undergoing an ion annihilation process. I will introduce our current research projects in the following slides. Number 1. For desensitized photoelectrochemical cell, the polymer organometallic catalyst assembly is bound to the surface of semiconductors, typically titanium dioxide as a photoanode for water oxidation. Chromophore excitation at the surface is followed by excited state electron injection into the conduction band of the semiconductor and then delivered through the external circuit to a photocathode for water reduction to hydrogen or carbon dioxide reduction to carbon monoxide. We developed a polymer assembly consisting of transition metal chromophores and anchors to the surface of metal oxide semiconductors, and then focus on the investigation of specific properties, including exciton and charge transport, surface functionalization, and the photoredox activity by using photophysical and photoelectrochemical techniques. Specifically, this slide shows one of our proposed polymer chromophore catalyst assembly. A is water oxidation catalyst, B is the organometallic anchoring group, C is the polymer backbone, and D is the semiconductor materials. This structure definitely allows us to study the photophysical and photoelectrochemical behaviors such as intra and intermolecular electron transfer processes and the interfacial dynamics between interfaces using ultra-fast temperature-dependent laser spectroscopy and SECM image. Number 2, we are interested in developing a hybrid fuel cell system. Global hydrogen production is still heavily reliant on conventional fossil fuels. Photoelectrochemical hydrogen production is an environmentally friendly process induced by sustainable solar power. Therefore, we develop a hybrid fuel cell system integrating photoelectrochemical reactors with a fuel cell power system. For developing a high-performance hybrid fuel cell system, we designed stable halide perovskite embedded into covalent organic framework through the in situ growth. Because the curves with stable crystalline porous structure could effectively prevent phase transition and the structural degradation of a halide perovskite. While halide perovskite serve as a photocatalyst, curves with different linkers and nuts act as light absorbers and an encapsulator. To effectively design and optimize the perovskite composite, we are using data-driven sciences and simultaneously utilizing the high-throughput SPECM screening technique to determine potential perovskite composite. For improving the efficiency and stability of a semiconductor photoelectrode, high-quality perovskite composite film can be achieved by controlling the crystallization, minimizing the pinholes, preserving surface defects, and facilitating charge carrier transfer. The systematically investigation of interfacial dynamics by ultra-fast transient spectroscopy is required. We designed a series of perovskite composite photoelectrodes with different architecture to illustrate photophysical and photoelectrochemical properties between interlayers. For the third current research project, currently there are some issues for the fourth generation light emitting diode. For example, rapid aging and the burning phenomenon in OLED devices, mass transfer and high cost in micro LEDs, high preparation temperature, and difficult to be compatible with large-scale roll-to-roll processes in QLED devices. We are then motivated to develop a low-cost, high-performance gel-type ECL devices containing a liquid-phase mixture of luminophores and electrolyte immersed in solid-state networks. For the potential problems, we cannot precisely control the crystallization of semiconductor materials. Besides, we don't understand charge recombination behavior, which can seriously affect the stability and the optoelectronic performance of the ECL devices. To address these issues, we use grazing incident wide-angle X-ray scattering to explore the crystallization kinetics of the materials, and utilize photophysical and photoelectrochemical technologies for an in-depth understanding of charge recombination dynamics in the perovskite emission layer, as well as other interlayers and interfaces. Another project is related to solar-assisted microbial photoelectrochemical cell, which is a hybrid system designed to enhance wastewater treatment and pollutant degradation. By combining bioelectrochemical and photoelectrochemical technologies, we aim to create a more efficient solar-driven processes for environmental remediation. In this project, we compare the performance of MR1 photoanode under light and dark conditions, demonstrating the solar illumination significantly enhances photocurrent density and accelerates the reduction of chemical oxygen demand. This synergy occurs as photoexcited holes in the valence band combine with bioelectrons from Schwann's MR1, paving the way for efficient simultaneous solar fuel production and pollutant degradation. I enjoy working with my collaborators and team members over the past several years. I appreciate all their significant contributions as well as all these internal and external financial supports. Thank you so much for your attention. I'm happy to answer any questions you may have.